Think of the model lifecycle as a governed loop, not a one-time build. From experimentation through validation, deployment, monitoring, updates, and retirement. ISO IEC 42001 asks us to connect technical decisions with approvals, evidence, and oversight. We've already built the foundation. ISO IEC 42001 concepts, governance responsibilities, risk controls, and data architecture. Now we connect those pieces to the model lifecycle, where design, training, deployment, monitoring, and evidence need to operate as one controlled system. ISO IEC 42001 does not stop at written AI policies. It expects those policies to become repeatable controls across the model lifecycle. Each model should move through defined stages: development, approval, deployment, monitoring, change, and retirement. At each stage, the architecture should capture who made the decision, what risk was assessed, what validation occurred, and what evidence was retained. This control backbone reduces drift, bias, security exposure, and undocumented retraining. It also makes audits easier, because responsible AI operation becomes part of daily engineering practice. Model development works best as a governed supply chain. Teams experiment, train, validate, test, register, approve, deploy, and then monitor the model in production. Along the way, the work creates evidence. Datasets used, code and model versions, performance metrics, risk reviews, approvals, and logs. Control gates are the checkpoints that stop weak, unapproved, or poorly documented models from moving forward. Monitoring then feeds decisions to retrain, adjust, or retire the model. Clear ownership across data science, engineering, risk, security, business, and operations keeps the lifecycle accountable. Model selection should not be a hallway decision based only on accuracy. Start by tying each experiment to the business purpose, system scope, and risk profile. Then track every serious candidate, including the model type, architecture, assumptions, constraints, and data choices. Compare candidates against the criteria that matter in production: performance, fairness, explainability, cost, latency, privacy, and maintainability. Finally, record why the chosen model best fits the objectives, and why alternatives were rejected, so reviewers and auditors can understand the decision. Reproducible training means a model is not just an artifact. It is the result of a fully traceable process. The pipeline should know exactly which dataset version, feature definitions, pre-processing steps, and sampling rules were used. It should also record the code commit, hyperparameters, library versions, container image, and compute configuration. Running training through a controlled orchestrator reduces one-off manual changes and inconsistent outcomes. The final model, evaluation report, and run metadata then become evidence for validation, incident investigation, retraining decisions, and certification audits. The model registry acts as the control tower for every model that might reach production. Each registered model gets a unique version, owner, purpose, risk level, and links back to the data, features, training run, hyperparameters, and evaluation evidence that produced it. As the model matures, its lifecycle state changes from experimental to candidate, validated, approved, deployed, deprecated, or retired. The registry also stores deployment packages and documentation. Access controls and audit logs help ensure that only authorized people can promote, modify, or release a model. Versioning in model governance is not just saving the trained model file. Every input that can change behavior needs its own identifier: the dataset snapshot, feature pipeline, source code, configuration, hyperparameters, evaluation results, documentation, and approvals. The goal is lineage. If a production prediction is questioned, you should be able to trace it back to the exact training data, validation evidence, and release decision that produced it. Deployment packages should be immutable, with locked dependencies. That supports change control, faster incident investigation, and reliable rollback when something goes wrong. Validation is the gate that turns model performance into a release decision. It should combine three kinds of evidence. First, technical measures: accuracy, calibration, latency, scalability, and reliability. Second, risk controls: fairness, robustness, explainability, privacy, security, safety, and misuse potential. Third, business readiness, user impact, operating procedures, cost, service levels, and fallback plans. The key discipline is to set acceptance thresholds before final validation begins. Otherwise, teams can rationalize weak results when deployment pressure is high. Clear thresholds make the decision auditable. Pass, conditionally accept with mitigation, or block release until the gap is fixed. Testing should build in layers. Start with unit tests for individual components. Then use integration and pipeline tests to confirm that data, features, model, and serving code work together. End-to-end tests validate the full user-facing path. From there, shift from engineering correctness to model behavior. Holdout, cross-validation, and out-of-time tests check whether performance generalizes. Robustness testing asks what happens when inputs are noisy, missing, shifted, or intentionally manipulated. For higher-risk systems, add fairness, privacy leakage, security, explainability, and adversarial evaluation. The goal is not just accuracy, it is confidence under real-world pressure. Production release should never be a handoff based on trust alone. The approval path starts by matching the model's risk tier to the required level of review. Higher criticality means stronger evidence, evaluation results, risk assessment, documentation, and readiness checks. Each role contributes a different control. Developers prepare the candidate. Validators challenge the evidence. Business or risk owners approve conditions. Operators release only what is authorized. Just as important, every decision, exception, and residual risk is recorded. That audit trail turns deployment into governed change, not an informal launch. Production deployment starts with one rule: only approved, immutable model packages should move forward. The registry, CI/CD pipeline, scans, and signing steps preserve that trusted state before anything reaches users. Release patterns then reduce risk. Shadow tests observe behavior without impact. Canaries expose limited traffic. Blue-green deployment enables fast switching. Champion-Challenger compares alternatives under control. Around runtime, enforce access control, secrets management, API security, environment separation, and detailed logging. Finally, rollback is not improvised. Define fallback modes, recovery triggers, and ownership before production exposure, so incidents become controlled responses, not surprises. Deployment is not the end. Monitoring is the feedback loop that keeps the model trustworthy. Track prediction quality, data drift, concept drift, fairness, latency, errors, and infrastructure health against thresholds tied to risk and business impact. When a metric moves from acceptable to warning or critical, alerts should create evidence, not just noise. Logs, metrics, incidents, human interventions, and model decisions show what happened and how the organization responded. That evidence then drives retraining, controlled changes, management review, and better decisions before small issues become operational failures. Model change management starts with a trigger: drift, a performance drop, new data, regulation, security events, business shifts, or user complaints. The key is not to react informally. Every change should move through impact assessment, controlled retraining or modification, regression testing, validation, approval, and documented release decisions. If the new version creates risk, rollback must restore a known good model with compatible data, code, and dependencies. When a model is no longer appropriate, retirement is governed as well. Decommission access, update inventories, preserve evidence, and notify affected stakeholders. Model lifecycle architecture is how AI stays controlled after experimentation ends. The registry anchors versions, lineage, approvals, packages, and audit evidence. Validation gates and change management help keep drift, bias, security issues, and undocumented updates from reaching production unchecked. Next, we apply the same control mindset to generative AI, LLMs, human oversight, explainability, and transparency by design.